I hope you find this helpful. And this is only one of many tools to help you get ready for the upcoming exam. And some other tools are, of course, take a look at the most recent exam. We'll do a few of the problems, but there's some that we don't do. Look at your recent quizzes, plus quiz 12. Quiz 12 is full of good problems. So take a look. Go see some instructors during office hours. Make sure you can do them. Go to class on Wednesday. It'll be a good review. All right, well, here we go. 17 problems, 2 hours, give or take. Let's see how we do. Find the summation from 0 to infinity of 3 to the n minus 2 to the n quantities squared over 10 to the n. Now, here we have a key word, find. And whenever we see the problem that says find, in particular when we're finding a sum, we know automatically one of three things is about to happen. Either it's geometric, and how do you know geometric? You're going to look at sum of something to the n power. So the n in the exponent is the key. It's going to be telescoping, and what's the key for telescoping? The key for telescoping is, I can write it as something minus something, where this is just slightly offset. Now, I'll talk a little bit about that in a moment. And the third thing you should look for is, can I recognize it as some sort of well-known Taylor series, which has been evaluated? So those are the only three. Okay, so once you see the question that says find, you know automatically I'm in one of these three camps. And we're going to do examples of all of these through the course of the various problems we're going to talk about. I said be careful here. You see, here's the thing, is we know what you know. And we kind of know what you're looking for. And so we like to have fun with that. We like to disguise things, make them look like harmless ducks when they're secretly geese in disguise. So just be careful, don't jump into things, but think about them. Now in our case, we're basically drawn to the fact that we see lots of n's, so it's probably going to be geometric. Now I say probably because it's not geometric yet. But what can we do? Well, we can expand the numerator. So this would be 3 to the n quantity squared minus 2 times 3 to the n times 2 to the n, and then plus 2 to the n quantity squared divided by 10 to the n. So we square it out, and then we say, hey, you know what we can do is we can really rewrite this sum as three sums. So I have 3 to the n quantity squared. Now 3 to the n quantity squared is the same as 3 squared to the n. In other words, I can change the order I take the powers in. And now I'm going to subtract 2, the summation, 0 to infinity. And then I have 3 to the n times 2 to the n. Well, that's the same as 3 times 2 to the n. And I still have that over 10 to the n. And plus summation 0 to infinity of, here will be 2 squared to the n over 10 to the n. So this becomes the summation, n equals 0 to infinity of 9/10. Because it's 3 squared, 9. And 9 to the n over 10 to the n is 9/10 to the n, minus 2, summation n equals 0 to infinity of 6/10 to the n, plus, rounding it out, summation n equals 0 to infinity of 4/10 to the n. All right, well, we're almost there. Now it's of the right form, geometric. In general, if I'm adding up a geometric sum, well, what do? Well, you figure out what's the first term. In our case, n equals 0, so that's 1. And you divide by 1 minus what you multiply by. Now, of course, geometric sums only work if the geometric term is smaller than 1 in absolute value. So if I had 10/9, I'd be toast. Wouldn't be able to sum it. But I don't have 10/9, so life is good. And in some sense, we can say, that's the answer. Well, but we can do better. 1 minus 9/10 is 1/10, and I flip that. This will give 10. Now 6/10 I should, of course, have simplified, and so that's really the same as 3/5. So here, 1 minus 3/5 is 2/5. Flip that, 5/2 times minus 2. So I get minus 2 times 5/2 is minus 5. The 2's will end up canceling out. And then the last sum, well, 4/10, again, could have been written as 2/5. 1 minus 2/5 is 3/5. Flip it, that's 5/3. So we end up with 5 plus 5/3. Well, that's 15/3 plus 5/3 is 20/3. And there's our answer. All right, so this was an example of a geometric sum. All right, good one for us to warm up on. Find the summation from n equals 2 to infinity of 4n divided by n squared minus 1 quantity squared. All right, well, it's not geometric. That one we can roll out right away. And also, it doesn't look like any of our Taylor series. You should memorize your Taylor series by heart. We'll see some examples of the Taylor series later on. So we're thinking telescoping. All right, if we're thinking telescoping, we have to find a way to rewrite this so it looks like something minus something. And hopefully it looks like something minus something, which is a good something minus something. So what's the idea? Well, the idea is to say, if we were doing integration, the way we would approach this problem is to actually approach it as a partial fractions. So n squared minus 1 is n plus 1 times n minus 1. So this is n plus 1 squared and minus 1 squared. So in partial fractions, this would be a over n plus 1 plus b over n plus 1 quantity squared plus c over n minus 1 plus d over n minus 1 quantity squared. Clear your denominators, and you get that 4n is equal to a times n plus 1 plus b, times n plus 1 n minus 1 squared, plus b times n minus 1 squared, plus c times n minus 1 n plus 1 squared, plus d times n plus 1 squared. On a side note, if you're getting nervous about this example, the partial fractions we would ask you to do on an exam would be easier than this. We do the hard ones during the practice so that we can give you the fun ones during the exam. Well, no, that's not true. All partial fraction problems are fun. So, all right. So, what's next? Well, you got to solve for a, b, c, and d. But of course, we can solve for some of them pretty quickly by choosing wisely. For example, choose n equals 1. You'll get 4 is equal to 0 plus 0 plus 0 plus 4 times d, leading us to conclude that d equals 1. If you plug in n equals negative 1, you're going to get 0. Then you're going to get negative 1 minus 1 squared. This actually turns out to be 4b. So that's negative 4 equals 4b, and then 0 and 0. So we can conclude that b is negative 1. All right, well, what else can we conclude? Well, let's suppose we look at n equals 0. Okay, that's 0 would equal, from the first term, I'd get a. From the second term, I'd get b. Well, that's really minus 1. From the third term, I'd get minus 1 times c minus c. From the last term, I'd get d, which is plus 1. So minus 1 plus 1 cancels. That says that now we know a and c are the same. But we don't know what a and c are. So let's see, what else can we do? Well, we can plug in another value, or we can do the other trick with partial fractions, which is to look at coefficients. So let's look at the coefficient of n cubed for a moment. On the left-hand side, we're like, darn it, there is no n cubed. Or is there? It's 0, because if there's no n cubed, that means there's nothing there. So that's 0. On the right-hand side, notice that there, the highest power of n is an n squared. So we're going to get nothing from that piece. We're going to get nothing from that piece. From the first piece, the highest power is n cubed. And in fact, the way you get n cubed is n, and then times a. So it's going to be simply a. And from here, you're going to get, again, the coefficient for n cubed would be 1 times your c. So by looking at the coefficient of n cubed, we get 0 equals a plus c. So in partial fractions, you do this sort of back and forth. Try good values, try good numbers, and then look at coefficients. But we also know that a and c are the same, but they add to 0. Well, that tells us that 2a is 0, which means that a and c are both 0. So That's the partial fractions part. Now, what does this allow us to conclude? It tells us that this becomes the sum from 2 to infinity of, we have 0 for A, B is minus 1, so C is 0, and D is plus 1. So I'm going to put the plus 1 first. So 1 over n minus 1 squared minus 1 over n plus 1 squared. So now we're in telescoping. Telescoping is something minus something. But in particular, they're offset things. So if we look at the first few terms, we're going to get, for n equals 1, we'll get 1 over 1 squared minus 1 over 3 squared. Go to the next one, we're going to get 1 over, so we're now at n equals 3, so that's 2 squared minus 1 over 4 squared. And the next term would be 1 over 3 squared minus 1 over 5 squared, and so forth, so on. Now, there's a couple things we should note. Now, when you're looking at a telescoping sum, one of the things you can look at is you can ask, what's happening to this piece? If this goes to 0, then that means it's pretty easy to figure out what happens, because that means everything will cancel off. The terms on the end are getting smaller and smaller, so you just have to figure out what at the start doesn't cancel. So in this case, we're in our happy situation. We'll see a problem where it doesn't go to 0. And so now we just have to figure out, well, how far do we need to go? Well, we have to figure out what's the offset. How far off are these two terms? Because that tells us how far we are from canceling. Now in our case, what's the offset? Well, it's 2, because if I have n plus 2 minus 1, I have n plus 1. Which means that if I want to cancel the 1 over 3 squared at the start, I go 2 terms down, and that will cancel there. So things will start canceling 2 terms down. So everything cancels off except the first pieces of 1 plus 1/4, which gives us a final answer of 5/4. And we're done. Whew. Okay, well, these are fun. All right. Using, oh my goodness, that 1/2 e to the x plus e to the negative x is the summation n equals 0 to infinity of x to the 2n over 2n factorial. Find the exact value for this expression. So, we know we're in a fine situation, but we even know which kind of fine situation we're in. They've basically told us what to do, in that we're going to be using Taylor series, or if you like, power series. They're the same thing. So I have this function, 1/2 e to the x plus e to the negative x, and I have that it's equal to this particular expression. Now, what do I need to do? Well, you might say, hey, wait a second, this one doesn't have an x. We'll deal with that in a moment here, but that's actually to our advantage for right now, because we get to pick x. So later on, we're going to make an x, and the way you make an x selection is you look over here and you say, well, where do you see something to the n? And if you don't see anything to the n, you can say that secretly, this is like 1 to the n sitting there. So what's going to happen is we're going to do something to this, and then we're going to plug in x equals 1. All right, so we kind of know what's going to happen. We're going to do something to our sum, plug in 1, and life will be good. Now, we haven't done enough yet, because if I plug in 1 right now, I'm just going to get 1 over 2n factorial. Okay, well, that's no good. That doesn't give me the n squared. So now we put on our thinking hats, and we say, what can we do? What can we do to bring things, or introduce n's, or move n's around? So there's a couple things that we can do. The basic things we can do is we can add and scale things, but the other two are the fun ones, which are we can differentiate and we can integrate. So when do we use them? Well, we integrate if we want to put things downstairs, because if you think about what happens when you integrate x to the 2n, you'd have x to 2n plus 1 divided by 2n plus 1. So integration is great for putting things downstairs. Differentiation puts things upstairs, because if I differentiate x to the 2n, a 2n comes down. It's going to be in the numerator. So in our case, since we want to end up with the n squared up here in the numerator, let's differentiate. So we're going to start with 1/2 e to the x plus e to the negative x, and equal to the sum, 0 to infinity, x to 2n over 2n factorial. So step 1 is differentiate. Okay, so take the derivative of both sides. Now the left-hand side is pretty easy. That's a half e to the x minus e to the minus x. On the right-hand side, it's also easy. Because if you have an infinite series, it's basically an infinite polynomial. That's how you should think of it. And so you take the derivative term by term. So 2n, x to 2n minus 1 over 2n factorial. And we say, fantastic, we've put an n there. We also have a 2, but 2's are easy to fix. We'd like to get an n squared. So we probably want to do it again. We shouldn't do it again yet because we want to fix that power. But that's also easy to fix that power. If I just want to bump the power up by 1, that just means I need another x. So here's the idea, is we're going to multiply both sides by x. So on the left-hand side, we get x over 2, e to the x minus e to the minus x. And on the right-hand side, when I multiply everything by x, every single term gets an extra x added on. So it's x to 2n. Okay, now what? Well, this technique is so nice, we're going to do it twice. We got one n down. The same thing will work again. So take the derivative with respect to x. And what do you get? Well, we have to do a product rule. 1/2 e to the x minus e to the minus x. And then plus x over 2 e to the x plus e to the minus x. Whew, getting longer. Is the summation n equals 0 to infinity of 2n times another 2n. Makes that 4n squared x to 2n minus 1 over 2n factorial. And now, what happens next? Well, actually, we're ready to go. Because we get to make a choice for x at some point. Because here there's no power of n, it means at some point we're going to choose x equals 1. So let's just choose it now. Because I've got the pieces I need. I have the n squared. I have that 2n factorial. 4 is a constant. We can deal with that. So let's plug in x equals 1 and see what we get. We get 1/2 e minus e to the minus 1, which is 1 over e, plus 1/2, and I'm going to have e plus 1 over e is equal to the summation from 0 to infinity of 4n squared, 1 to the 2n minus 1 over 2n factorial. And we're almost free. We just need to observe 1 to the 2n minus 1. Okay, that's just 1. Don't need to write it down. On the other side, the 1 over e's cancel, so we end up getting e. And the last thing is, how do we handle that 4? And the way we handle it is divide both sides by 4. So we can conclude that 1/4 times e is the summation, n equals 0 to infinity of n squared over 2n factorial. And that's the answer. All right, well, that's good. Whew, that one was fun. I liked that one. Students last semester, not so much. But I loved it. It was great. So, find the interval of convergence for the power series n times 4x minus 9 to the n divided by 7 to the n over this, 7 to the n times square root of n cubed plus n. Now, when you find intervals of convergence and things like that, don't worry about where you start your sum. Don't like, oh my gosh, we're starting at 17. That really changes things. It changes nothing. Because when we're talking about convergence, it doesn't matter where you start. Convergence always matters what happens at the end, towards the infinity, and that's a long ways away from 17. So the first 100 terms, the first million terms, they don't matter in the long run. All right, well, now we have to figure out interval of convergence. Well, let's start. So the first thing to figure out is we want to find the radius of convergence. And the way we do that is we apply either the root or the ratio test. So our process here is we're going to find the radius, and this is going to be done by doing root or the ratio. You can do either in some cases. In some problems you have to be specific. And then once we figured that out, we're almost home free, and we have to deal with the endpoints when we're dealing with the interval. Okay, so those are sort of the things that we're going to do. Now when you test the endpoints, you're going to have to do something else. Root and ratio fail. So, well, it depends. We don't know. We'll get there in a few moments. I don't know, do you have a preference? Root or ratio test? Root? Yeah. Root. You know, it's like that character from Guardians of the Galaxy. And every time, just goes, I am root. Like, yeah, okay, all right. All right, you're the root test. All right, good. So let's figure this out. This is our a sub n. So we're going to take a look at the limit as n goes to infinity of the absolute value of a sub n to the 1 over n. Now, in this case, this is the limit as n goes to infinity of n, absolute value of 4x minus 9 to the 1 over n, over 7 to the n to the 1 over n is just 7. And then I have n cubed plus n to the 1/2 to the 1 over n. All right. Oh, whoops. I forgot to put my n here. There we go. Got to make sure we have it all there. That's getting kind of messy. Let's clean that up. So this is limit as n goes to infinity. First off, the absolute value of 4x minus 9 and 7, that's just going to be 4x, absolute value of 4x minus 9 and 7. Then I have this other stuff, n to the 1 over n. Then I have the stuff down here. Now, we have to think about this for a moment. And, well, what are some things you can do? You can interchange the order if you want. N cubed plus n to the 1 over n to the 1/2. Now, we're not going to be super strict about verifying things, but you should have some intuition about what's happening. What happens to n to the 1 over n? Do you know that limit? Yeah, this goes to 1. Okay, so that one's easy to see. Let's talk about this denominator. When you look at it, it's not so obvious what happens to that. But probably if you had to guess, what do you think? Okay, I'm going to ask you to guess. What do you think it goes to? Yeah, okay, good. I mean, you got good intuition. It should be about 1, because here we go. We'll actually make this quasi-rigorous. N cubed plus n to the 1 over n. Well, look, that's going to be bigger than just n cubed to the 1 over n. And n cubed to the 1 over n definitely goes to 1, because it's n to the 1 over n cubed. So this is going towards 1. On the other hand, what is it smaller than? Well, it's smaller than 2 n cubed to the 1 over n. But now, 2 to the 1 over n is also going to be going to 1, and n cubed to the 1 over n still goes to 1, so it also goes to 1. So yes, this does go to 1 as well, which means that at the end of the process, what's our limit? This is absolute value of 4x minus 9 over 7. That's not quite the radius, it's not the interval, but we're so close. Because we remember how the root and the ratio test work. It works by saying whatever the limit is, as long as it's less than 1, we're going to converge. In fact, it's a little bit stronger. As long as we're less than 1, we're going to converge. And if we're bigger than 1, we're going to diverge. The equals to 1, it's interesting. More work, more work. So, from here, we can conclude it's going to converge when 4x minus 9, the absolute value, is less than 7, or negative 7 is less than 4x minus 9, is less than positive 7. All right, add 9 to everything. 2 is less than 4x, is less than 16. And divide everything by 2 again. By 4. 1/2 is less than x, is less than 8. So, 4, yeah. Oh my gosh. Yeah, 8 didn't feel right. Good. 1/2 less than x, less than 4. We're almost there. So what we can say for sure is if we're between 1/2 and 4, we definitely converge. And we can say if I'm below 1/2 or I'm above 4, definitely diverge. The only thing we don't know is the endpoints. So now we come to our endpoints. And for endpoints, we have to do those separately. In fact, we'll probably have to do two things. So let's do the endpoint of 1/2. So what happens at x equals 1/2? We're going to get the summation from 17 to infinity. And when we plug in a half, we're going to get 2 minus 9, which is negative 7. So I'm going to get n, negative 7 to the n, divided by 7 to the n, times the square root of n cubed plus n, which we can clean up because we both have 7 to the n upstairs and downstairs. So we have the summation n equals 17 to infinity of minus 1 to the n times n over cubed root of n cubed plus n. What test can we use here? Alternating series test, because it's alternating. Now, if you have an alternating series test, you have to check two things. Is it alternating? And does it go to 0 reasonably? And it alternates. And then we just look and say which is bigger, the numerator or the denominator in the long run. Well, in the long run, the denominator will win. It's a higher power. So what we can conclude is this alternates. Terms go to 0. So by alternating series test, this converges. Which means that we're going to include our endpoint of a half. So a half will be in our interval. So our answer is going to be a half less than or equal to x. And then we just have to figure out what goes over there for the 4. So we don't care how it converges. In other words, we don't care if it's conditional conversion or absolute. We just care, does it converge? All right, not a lot of space left here, but let's try the other endpoint, x equals 4. Now, if you plug in x equals 4, what you'll see happen is we're going to get 16 minus 9, which is 7. That's 7 to the n. There's a 7 to the n already, so if we simplify, we'll just end up with n over cubed root of n cubed plus n. Now, this is a sum where there's no alternating sign. Everything's positive. So we're going to think about, okay, how do we find the answer to this sum? And the key for this kind of thing is to say, look, there's some noise here. That plus n. And what you do is you say, look, ignore the smaller order terms. So if we can do a limit comparison test. So a limit comparison test says, drop everything but the highest order terms, and whatever happens to that sum happens to your original sum. So we're going to do a limit comparison test with sum n equals 17 to infinity, n over square root of n cubed, which of course is the sum n equals 17 to infinity. If we simplify this, what do you end up with? 1 over square root of n. Now, does this sum converge? And the answer is no, it diverges. How do we know? Because it is a p-series. This is a p-series, and here p equals a half, which is less than 1. Which means we do not include the endpoint of 4, so our answer is 1/2 less than or equal to x less than 4. So if you're asked to find the interval, remember, you have to get the endpoints. If you don't need the endpoints, you don't have to check them. Now, here's an example. Find the center and radius of convergence for the power series n factorial x plus 2 to the n divided by 4 times n to the n. This explicitly is trying to say, don't worry about the endpoints, which probably means it's hard to figure out the endpoints. But that's okay, we don't mind. If it's less work for us, that's great. I'm sure there's still plenty of work left to do. Well, what test should we use here? We should use the ratio test. And what gives it away that this is a ratio test problem? Yeah, factorial. If you see a factorial, you better think ratio test. If there's some question about convergence going on and you see a factorial, it's automatic. That's just the way it is. So we're going to take a limit. N tends to infinity. A sub n plus 1 over a sub n. Normally we throw in the absolute values, but in this case, I guess we do have to include absolute values because the x plus 2 could be negative. Yeah, I forgot about that x plus 2 there. So this is the limit as n goes to infinity of, and here's the hard step. Well, for some people it's hard. Remembering how do you get to a sub n plus 1? And the answer is just everywhere you see an n, put an n plus 1. And use parentheses if you need it. Parentheses are your friends. They will help save a point. And every point matters. Got to get all the points. So n plus 1 factorial, absolute value of x plus 2 to the n plus 1 over 4 times n plus 1 to the power n plus 1. And we're going to have times a sub n, which, well, you flip it because it's downstairs. 4n to the n over n factorial, absolute value of x plus 2 to the n. Now, you should see things that look like they should cancel. And because they will cancel. Absolute value of x plus 2 to the n, most of those will cancel. So that's good. Now, that's the easy one. Some things you have to do a little bit. Oh, I guess the 4. Yeah. The 4 is there. It's just sort of as a red herring. It doesn't really have much effect. Now, the factorials we want to cancel, and we can't quite cancel yet, but they're really close. N plus 1 factorial looks an awful lot like n factorial. In fact, it's really like n factorial with one more piece. So what you do is you pull off that extra piece. So limit n goes to infinity, n plus 1 times n factorial. We still have that absolute value of x plus 2. We still have that n to the n. And downstairs we have an n factorial. And we have an n plus 1 to the n plus 1. Well, I really want to mix it with n to the n, so I'd want it to have n plus 1 to the n, but that leaves me with one n plus 1 left over. But that's all right. I could use an extra n plus 1. So the n plus 1 upstairs came from pulling it off the factorial. The n plus 1 downstairs came from that exponent. And now we do some even more cancellation. So we're in great shape. N plus 1s cancel, n factorials cancel, and we're to the following. This is the limit, as n tends to infinity, of absolute value of x plus 2, which is a constant. We could pull it out of our limit. And then you have n over n plus 1 to the n. Now that doesn't quite look like anything we've done, but there's an alternative. We could write this as something slightly different. Because one of our goals is we know things. And what we want to do is take what we know and say, can I adapt the current thing to fit what we know? Now, what do I say we know things? Well, here's something that we do know. 1 plus 1 over n to the n, that we know what it converges to. That always converges to e. In general, 1 plus t over n to the n converges to e to the t. But most often, this is the one we're going to see. It kind of looks like this expression, because another way to write 1 plus 1 over n is n plus 1 over n. And so if I see 1 plus 1 over n, I can convert it to n plus 1 over n, or vice versa. All right, well, that's sort of upside down, which says, oh, write it upside down. So this is really 1 over n plus 1 over n to the n. So if I move it down, I flip, and now I say perfect, because I know what this converges to. So this is absolute value of x plus 2 times 1 over square root of e. And to converge, we need to be less than 1. So rewriting this, we get that this says absolute value of x plus 2 is less than square root of e. And at this point, we can almost read off our answer. Because what do we mean when we talk about things like the center of convergence and the radius of convergence? Well, typically what we mean is we have x minus a less than r. That's what we want. And a is the middle, and r is how far we go in each direction. And that's going to be our interval of convergence. So the center is the center point, r is how far we go in each direction. So if I can write my expression in this format, I can read off my center and my radius. Now, we're almost there. In fact, really the only thing is, instead of x plus 2, we can think of it as x minus negative 2. And now we say, aha, we can read off our answers. Minus 2 and square root of e. So minus 2 is our center. Square root of e is our radius. And that's the answer. We're done. Because that's all we needed to find for this, was the center and the radius. All right. Yes?
Why is it square root of v?
Why is it square root of v? Oh, it's not square root of v. Man, you are right. I was thinking of some other problem. It's just e. E! I made a mistake. Thanks for pointing that out. All right. I was confusing it with, there's another problem where I get square root of v. Too many problems. Okay. Well, thanks for pointing that out. Determine if the sum from 1 to infinity of 3 to the n times n factorial times n to the n over 4 to the n times 2n factorial diverges, conditionally converges, or absolutely converges. Ooh, it's one of these. Now, we can roll out something right away. Which one can we roll out without any work? The answer is we can roll out conditional right away. Conditional convergence can only happen if you have both positive and negative terms. If you don't have both positive and negative terms, it's impossible to be conditionally convergent. So that's good. It's either divergent or it's absolutely convergent. All right, well, that's some progress. How do we go further? How do we figure out whether it's divergent or absolutely convergent? Well, we use the test. And so you might notice there's things that we're going to keep doing over and over again. So one of the things you're going to keep seeing us do over and over today are tests. Tests for convergence. How do we figure out whether or not things converge? Because that's been a very huge part of our last few weeks. All right, so here we go. Here's our a sub n. So we're going to take the limit as n goes to infinity of a sub n plus 1 divided by a sub n. Here, I really don't need absolute value because the terms can never be negative. So this becomes the limit. N goes to infinity, and 3 to the n plus 1, n plus 1 factorial, n plus 1 to the n plus 1, divided by 4 to the n plus 1, and then here 2 parenthesis n plus 1 parenthesis. So I really want to remember that it's everywhere there's an n, it's n plus 1. Because it's really tempting to write down 2n plus 1 and forget that the 2 should go to the plus 1 as well. All right, then we have the a sub n term, which means you just flip it. All right, 4 to the n over times 2n factorial over 3 to the n, n factorial, n to the n. Now, the process is going to be really similar. We're going to say, does anything cancel? We can certainly cancel the 3 to the n's, mostly cancel. The 4 to the n's, mostly cancel. So that gives us a 3/4. And then we're going to start pulling things off. So let's see what we can pull off. Well, to get an n factorial to cancel, I'm going to pull off a single n plus 1. And I'll have n factorial. Again, in anticipation, we're going to do something similar to the last problem, where I'm going to have this n plus 1 to the power n plus 1. I really want to make it to a power n so I can mix and match these two. So I'm going to put this as n plus 1 times n plus 1 to the n. And then I have a 2n factorial. So that's the upstairs. Downstairs, I forgot the 3. So there we go, 3 and the 4. Then we have 2n plus 1 factorial, which is really 2n plus 2 factorial. So we start pulling terms off. 2n plus 2, 2n plus 1, 2n, and now I'm good to go, factorial. So that's the 2n plus 1 factorial became 2n plus 2 times 2n plus 1 times 2n factorial. Then I still have the n factorial and the n to the n. And now we can continue our fun does it cancel game. And 2n factorials, does it cancel? Yes, it does. N factorial, does it cancel? Yes, it does. N to the n, does it cancel? No, because it's n to the n and n plus 1 to the n. There is a little bit more you can cancel, which is to note that 2n plus 2 is 2 times n plus 1. And so if you make that substitution, you get another cancellation. And so where are we at? Well, we're at the limit. As n goes to infinity, we have the 3 and the 4. What's left upstairs? We have an n plus 1, and then we have an n plus 1 to the n. Downstairs, we already grabbed the 4, we have a 2n plus 1, and then we have an n to the n. So this becomes the limit, as n goes to infinity, 3/4 n plus 1 over 2n plus 1, and n plus 1 over n to the n. The 2? Oh yeah, you're right, the 2. Thank you. That's easy to fix. Double check your work. Yes. Or don't try to do 20 problems. Just do 6. Just do the right number. All right. Okay. Well, have I forgotten anything else? No, don't think so. All right. Well, where are we at? What happens to n plus 1 over 2n plus 1? 1 over 2. It's a polynomial over a polynomial. You look at the leading coefficients. So that would go to 1 over 2. What happens to n plus 1 over n to the n power? Goes to e. This is, again, it's 1 plus 1 over n to the n. And that goes to e. So, where are we? This becomes the limit. Well, actually, we don't have to do a limit anymore. We found the limit. So it's going to be 3/8 times 1/2 times e. So that becomes 3e divided by 16. Well, what happens to that? What is 3e divided by 16? Is it bigger than 1 or is it less than 1? It's less than 1. Okay. Good. Well, so what's our conclusion? So, if our limit is less than 1, this will converge. Okay, well, which means it's not divergent, so it must be absolutely convergent. All right. Interesting, interesting. Good. Well, any questions on this one? Now, one of the things is it's possible that you don't have to justify things. And like if you look at the exam from last semester, there was number 1 where it just said, hey, just circle your answer. Don't even bother justifying. So after a while, you want to get a little bit faster at spotting things. And with practice, a lot of times, these become pretty straightforward. Okay, so, well, find the interval of convergence. Summation from 7 to infinity, arctangent of n to the n times x to the n over n squared. All right, well, I think there's a particular test that should work pretty well here, which is the root test. So let's do the root test. So that's our a sub n. So we're going to take a limit as n goes to infinity of absolute value of a sub n to the 1 over n. So this is the limit as n goes to infinity of arctangent of n to the 1 over n is arctangent of n. X to the n to the 1 over n, and of course there's an absolute value involved, is just absolute value of x. And downstairs I have n squared to the 1 over n, which is really the same as n to the 1 over n quantity squared. Well, this is the limit we can find because n to the 1 over n goes to 1. We've done that. Absolute value of x is just absolute value of x. What happens to arctangent as you head to infinity? Goes to pi halves, pi over 2. So this is pi halves absolute value of x. And this will converge when this is less than 1. And therefore, we can conclude that this will converge when absolute value of x is less than 2 over pi. So we're in good shape. We now know that it will definitely converge for negative 2 over pi less than x less than 2 over pi. The only thing that we don't know yet is the endpoints. So the question is, should these be less than signs or should they be less than or equal to signs? And there's 2 of these, so we have to go through and do them both. So let's go ahead and see if we can figure this out. All right. So let's plug in x equals negative 2 over pi. So I have the summation n equals 7 to infinity of arctangent of n to the n times negative 2 over pi to the n over n squared. Now, normally we'd be in trouble here. But we are not normal because we know arctangent. We spent a lot of time with arctangent. And in particular, we know that asymptotically it approaches pi halves, but it's good to know not only how does it approach pi halves, it's good to know not just that it approaches pi halves, but how it approaches pi halves. So if you were to graph the arctangent function, it approaches it from below. So what can we say? Well, let's see what happens if we bound this. So in other words, I want to get something slightly bigger. So one thing we can say is suppose for a moment we ignore the sign. So arctangent of n to the n, so I'm going to look at the absolute value of this, 2 over pi to the n, is less than, arctangent of n is less than pi over 2. So pi over 2 to the n, 2 over pi to the n. Well, what can we say about pi over 2 times 2 over pi? Well, it's 1. So, we can conclude that the terms are bounded, if we throw in the over n squared, by 1 over n squared. So this is a case where if we now look at the absolute value, so we drop the sign, we can do a comparison test. We can compare it to 1 over n squared. What do we know about the sum of 1 over n squared? Converges because it's a p-series. So it's a p-series, p equals 2, so it's a convergent series. So by comparison test, we know that this is absolutely convergent. Now, the reason I throw in the word absolutely is really we're looking at what happens if we drop the sign, because if we don't worry about the negative sign. Now that's at x equals negative 2 over pi, and just the same thing happens at the other end. So the same thing happens at x equals positive 2 over pi. And so that means that at the endpoints we're going to converge, so these should be included. So they should be less than or equal to. So that's the answer. And again, this one's slightly more subtle, but we like to do the subtle ones here. All right. Good. A fun one. Let's find p sub 2 of x. This is the second order Taylor polynomial for the function f of x, which is e to the power x to the 3/2 minus 1 centered at 1. And then we're going to use this to estimate e to the 3/2 to the 3/2 minus 1. Now you might say, why would we want to estimate that? And the answer is because you want to get full points on the test. That's why. That's a good reason. Okay, I'll buy that. So what do we have? Now there's a temptation here to say, oh, this is like e to the x, but I'm just using x to the 3/2 here. So the temptation is to say, I know that e to the z, that's the summation from 0 to infinity of z to the k over k factorial. So e to the x to the 3/2 minus 1, that's the summation, k equals 0 to infinity, of x to the 3/2 minus 1 to the k over k factorial. Now, two things. It's absolutely true. There's nothing wrong with that, but that's not finding the power series. See, the power series will not have this exponent 3/2 there. So that's the thing. Yeah, you can do that, but it's not helping you get closer to your answer. So we got to do something a little bit different here. And so what are we going to do? Well, p sub 2 of x, the second order Taylor polynomial, says, look, we're really going to start and look at our function. So generically speaking, p2 of x, what does it look like? Well, it's going to look like our function at where we're centered at. In this case, we're at 1. So it'd be f at 1 plus the derivative at 1 times x minus 1 over 1 factorial plus the second derivative evaluated at 1 times x minus 1 squared over 2 factorial. Now we can stop here because that's p sub 2. That says stop at the second derivative. If it was p sub 3, what would be the next term? Well, if it was p sub 3, the next term would be the third derivative evaluated at 1, x minus 1 cubed divided by 3 factorial. Of course, that's if we were doing p sub 3, and we're not. So this question is really asking us to do what? Well, it's saying find your f1, your f prime 1, your f double prime 1, and plug it into the formula. So do you know how to do the process is what this question becomes. So let's go ahead and go through the process. So we have our function f of x is e to the x to the 3 halves minus 1. We take our first derivative, f prime of x. What's our derivative? Well, it's e to something. So the derivative of e to something is e to that something. Then what do you do? Times the derivative of the something, times the derivative of the inside, which would be 3 halves x to the 1 half. So the derivative of x to the 3 halves is x to the 1 half. Now, we need to keep going till we get the second derivative. So the second derivative, well, we can use the product rule. So 3 halves times the derivative of x to the 1 half. So 3 halves times 1 half, x to the minus 1 half. Then the other function, untouched, e to the x to 3 halves minus 1. Plus the first function, 3 halves x to the 1 half stays alone. Then I times it by the derivative of e to the x to the 3 halves minus 1, which very conveniently I actually have written down right here. Whoops, sorry. That's 3 halves. Come back. There you go. 3 halves x to the 1 half, e to the x to the 3 halves minus 1. Now, you might say, oh, that looks terrible. Do we have to simplify that? And the answer is no. Because what do we have to do? We have to plug in 1. Now, the hope is that 1 is a nice number. It turns out, true story, 1 is nice. So, 1 to the 3 halves is 1. 1 minus 1 is 0. E to the 0 is 1. F prime of 1, well, it'll be 3 halves times 1 to the 1 half, which is 1, times e to the 1 to 3 halves minus 1. That's e to the 0, which is 1. So 3 halves times 1 gives us 3 halves. F double prime of 1, we have 3 halves times 1 half times what will become 1, because it's 1 to the minus a half, and then e to the 0 again. So that's 3/4 from that term. Then from our next term, we're going to have 3 halves times 1 times 3 halves times 1, which is 9/4. And 3/4 plus 9/4 is 12/4, also known as 3. So we get that our polynomial p sub 2 of x is equal to f sub 1, which is 1, plus 3 halves times x minus 1, plus 3 times x minus 1 squared over 2 factorial, which is also 3 halves x minus 1 squared. So that's the answer to the first part. The answer to the second part is we want to use this to estimate e to the 3 halves to the 3 halves minus 1. So e to the 3 halves raised to the power of 3 halves minus 1, that would be what would happen if we plugged in f at 3 halves. That's approximately what happens if we plug 3 halves into our Taylor polynomial. So that becomes 1 plus 3 halves times 3 halves minus 1. Well, that's a half, plus 3 halves times 3 halves minus 1, which is a half, squared. Or 1 plus 3/4 plus 3/8. Write this all over 8s. Now, you're wondering, do you need to simplify? And the answer is, let's see what the problem says. If the problem says to simplify, simplify. If it doesn't, don't. So put everything over 8, you get 8 over 8, 6 over 8, 3 over 8, giving us the final answer of 17/8. And that's the approximation. Is it good? I don't know. Maybe. Seems reasonable. All right. So, doing good. About halfway through, and use up about half our time. Use the first 3 non-zero terms of the Taylor series of the cubed root of 8 plus x cubed centered at 0 to estimate the integral from 0 to 1 of the cubed root of 8 plus x cubed. So this is one of the applications of Taylor series. So there's a couple of applications of Taylor series we're going to talk about. One of them is to say, suppose you have something you just don't know how to integrate. Well, write what you're trying to integrate as a Taylor series, and then just pick a first couple of terms, and then life is good. So this is that kind of application. We'll see the other application in a little bit. All right, so let's think about what to do here. So there's 2 things that we can do. One thing that we can do is to actually go through and take derivatives and see, okay, let's see what the derivatives tell us, and that will give us what we need. However, I suspect it will take us a while if we do that, because the cubed root, that x cubed makes me nervous. That'll take us a while to actually get all the terms we need. The other thing to do is to say, maybe there's a better way. So, on our list of things to know, there's something called the binomial series. So what's that? It says that 1 minus z to the alpha is equal to, so 1 minus z, that's 1 plus z, I think, sorry. 1 plus z to the power alpha is the summation, k equals 0 to infinity, of alpha, choose k, z to the k. So that was on our list of series to know. I think you've covered this, have you? Or you're about to cover it? One of those. All right. It should look kind of familiar. This should kind of feel like, I thought we learned this back when we were in pre-college, pre-calculus, algebra days. We did something like this. And the answer is, you did do something like this, but you did it when alpha was like 1 plus z squared. And like alpha is 2 or alpha equals 3. And now we're going to say, you can do it with other things too. So the question is, what is alpha choose k? What does this symbol mean? Well, this is a great symbol. So what it says is you're going to write down alpha times it by alpha minus 1 times by alpha minus 2 and so forth until you've gotten up to k terms. So there's actually k things multiplying upstairs. And downstairs, you do the same thing. K minus 1, k minus 2. Until you get to k terms, it turns out it's k factorial. So it's just, you multiply starting at alpha, go down by 1 until you get to k terms upstairs, you multiply k factorial downstairs. All right. Why do I point this out? So, if you look at the cubed root of 8 plus x cubed, what's another way to write this? This is 8 plus x cubed to the 1/3. That's not too surprising. One of our goals is trying to say, okay, can we learn to sort of fit the mold? So I want to fit this mold over here. So I want to make it look like 1 plus something to a power. Now the z can be whatever I need it to be, but I need to make it look like a 1 plus. So with that in mind, I can say, well, I could pull out an 8. All right, this has 1 plus x cubed over 8. All to the 1/3. And 8 to the 1/3 turns out to be a nice number. So it's 2, 1 plus x cubed over 8 to the 1/3. And now I say, I'm fitting the mold. I can say the following. This 1/3, that's my alpha. The x cubed over 8, that's my z. So now that I'm here, I can finish this up and say that the power series is 2, the summation, k equals 0 to infinity, of 1/3, choose k, times x cubed divided by 8 to the k power. So where the alpha is 1/3, so I put in alpha is 1/3. Z is x cubed over 8, so I put in z equals x cubed over 8. So that's the series. Now, how do I use this? Well, I want to find the first 3 non-zero terms. So I just start plugging in the terms. So plug in k equals 0. 1/3, choose 0. Well, I don't do any multiplying. And if you don't do any multiplying, then you get 1. It's called the empty product. So I'm going to have the 2 on the outside. So this will be 1. And then I'm going to have x cubed over 8 to the 0, which is 1. So this is the k equals 0 term. Not very exciting, but you got to put it in there. And in some sense, it's kind of what you expect, because if you plugged in x equals 0, you should get 8 to the 1/3, which is 2. So there you see, you get 2 times 1. Now you go to your next term. Okay, so the next term, we're going to have k equals 1. So I'm going to get 1/3, choose 1, which is 1/3. Well, that's one term, so I'm done. Downstairs I get 1, which is one term, I'm done. So 1/3 times x cubed over 8, because that's to the 1 power. There's my k equals 1. So there's my second non-zero term. Now I go to my next non-zero term. So that's going to be k equals 2. 1/3, choose 2. Well, upstairs I have 1/3. So times it by 1/3 minus 1, which is negative 2/3. Then I'm going to divide it by, start with 2 times 1. So that's minus 2/9 from upstairs times a half, which is negative 1/9. So minus 1/9, that's the coefficient 1/3, choose k, and times x cubed over 8 squared. And then there's other terms, but I just need to grab the first 3. So we're almost to the point where we're ready to actually do what we were asked. So let's see where we're at. Okay, so we are at, if I multiply the 2 through, so that we have the cubed root of 8 plus x cubed is 2. Then here, when I multiply the 2 in, I'll have 1/3 times a 4th. That'll give 1/12 x cubed. And here, when I multiply the 2 in, well, 8 will be squared, so that'll be 64. Then the 2 will give 32. So minus 1 over 9 times 32 and x to the 6. And there's other terms as well. So where are we going? We want to estimate that integral. So the integral from 0 to 1 of the cubed root of 8 plus x cubed dx is about the integral from 0 to 1 of 2 plus 1/12 x cubed minus 1 over 9 times 32 times x to the 6. And then we just stop it. So that's where the approximation comes from, because we say we're only going to go a couple of terms in. And now we do the integral. So that'll be 2x plus 1 over 48 x to the 4th minus 1 over 9 times 32 times 7 x to the 7th. Evaluated from 0 to 1. And plug in 0, you get 0. Plug in 1, you get the coefficients. 2, 1 over 48, and minus 1 over 9 times 32 times 7. And that's our approximation. All right. So this one's a little bit more challenging one. But it's a good one to do. It's a good one to do. There was a problem not too far off from this on the final exam last year, or last semester. So it's a good one to be able to do. All right. Take a breather, a little bit of a cool down break here. So find the exact value of the summation n equals 1, cosine squared pi over n minus cosine squared pi over n plus 1. So this one came from the final exam last semester. How bad could it be? Well, it's kind of bad. A pretty low average on this one. We weren't expecting that. But we kind of know what it is. Because we see the word find, we say, okay, so it's got to be one of three things. It's got to be either geometric telescoping or some sort of a Taylor series. And we see it set up to be telescoping because we have this subtraction going on where there's an offset. So we know it should be telescoping. So what makes this hard? Well, what makes this hard is look at what's happening to this term. This is not going to 0. So when your last term doesn't go to 0, you have to be careful. So what do you do when it doesn't go to 0? Well, what you do is you look at what are called partial sums. So in this case, what does that mean? It means we're going to sum from 1, but not go all the way to infinity. We're going to stop somewhere, n. Cosine squared pi over n minus cosine squared pi over n plus 1. So we're going to take that sum. Now, we're still going to get cancellation. In fact, that's why the telescoping series are so nice. It's not that cancellation is not going to happen. It's just that we have to be careful about what's left over after we cancel. See, previously when things went to 0, we would see that the n was getting small, so it's like, well, look, it's going to take care of itself. Don't worry about it. But now that's no longer the case. So we say, well, what does the n become? So oftentimes it helps to sort of write down the first few terms to see what's happening. Now, as you write down the first few terms, we're going to see, and this should not surprise us, that cancellation happens pretty quickly because the difference here is n and n plus 1, which means that when we're looking for what cancels, we only need to look at the next term. So the consecutive terms will start to cancel. And this will happen all the way down up until we get near the end. So the last term, well, that's when I'm at capital N, cosine squared pi over capital N minus cosine squared pi over capital N plus 1. So this will cancel with the next term. This one will cancel with the one that's before. We didn't write it down, which means that when we look at the partial sum, we're going to be left with cosine squared of pi, the very first term, minus cosine squared pi over capital N plus 1. Now we're almost done. Because if you know what a partial sum is, you just say, now let your n, your upper bound, get big. Let it go to infinity. So the cosine squared of pi, that's not going to change because there's no capital N. Cosine of pi is negative 1. And so this will be negative 1 quantity squared, which means the first term is 1. Subtract. Then we say, what happens to this as n goes to infinity? Well, this is going to get large downstairs, so I'm going to get a small number on the inside. It's going to 0. So it's cosine of 0, which is 1, and I square it. So it's 1 minus 1, giving us a final answer of 0. So that's the answer. It all cancels out. So, good. This time, let's have everyone get full points on these types of questions. Okay, back to the fun stuff, applications. I said there were two applications. So one application is to say, well, look, if I have a Taylor series, I can use it to approximate. In fact, we've done it in two different ways. We said, use a Taylor series, find the first couple of terms, get an approximation to a function. And then we said, look, here's a Taylor series, take the first couple of terms, get an approximation to the integral. But now we're going to use sort of the other application of Taylor series, which is to say, where are Taylor series coming from? If we think about what Taylor series are coming from, we say, you know, our function f of x, if we think of the Taylor series, that's a sum from 0 to infinity of the kth derivative evaluated at our center point. Now, in our case, it's 0. It doesn't have to be. Divided by k factorial x minus 0 to the k. So, in essence, what we should think of is that our Taylor series, it's storing information about derivatives. So that's sort of the key. Taylor series store information about derivatives. So if it's possible for us to get a Taylor series in some fashion, and we know what it is, now we've found all the derivatives. And when I say all the derivatives, I really mean literally all of them, all the way down. So Let's do this. We have this function. F of x is x to the 7th sine of 2x plus x to the 6th cosine of 3x. And you want to find the 20th derivative evaluated at 0. So here's what we're going to do. Our process is find the Taylor series expression for this. And we'll talk about how we find it. Once we have that, we're going to look at that and we're going to say, that's storing all our derivatives. Let's go grab the one we want. So, how do we find it? Well, the wrong way to find it is actually to start by taking derivatives and evaluating. Look, that's hopeless. Forget it. Forget it. You don't want to do it. You want to be smart. You want to have hope. Okay. The smart thing is to say, I know a handful of basic Taylor series. So the handful of basic Taylor series you should know, have committed to memory, e to the x, sum k equals 0 to infinity, x to k over k factorial. You should know sine of x, summation k equals 0 to infinity, negative 1 to the k, x to the 2k plus 1 over 2k plus 1 factorial, cosine of x, summation k equals 0 to infinity of minus 1 to the k, x to the 2k over 2k factorial. And I'll throw in 1 over 1 minus x. But we've already mentioned this indirectly. That's the sum k equals 0 to infinity of x to the k. These are ones you should just know. And we expect you to know them. We say, okay, now here are the ones that you know. Use these to figure out what's going on. So, how do we do this? Well, we fit the molds. So we have x to the 7th sine of 2x. What can we do to that? Well, x to the 7th, that's fine. In fact, we love x to the 7th. Think of Taylor series like polynomials. And x to the 7th is just a polynomial. So it's a great polynomial for us to work with. So we're happy for it to come along. It's the sign that we have to convert. So now we say, okay, I've got to use what I know. Now the thing is, I just have to make the adjustment. This is sine of x. I want sine of 2x. Well, it's an easy adjustment. I just update this to be 2x, and if I update this to be 2x, I just have to update the corresponding part over here to be 2x. It's a matter of changing your names so they're consistent. Or, as you might say, what's in the box? Well, right now it's called x, but we can call it whatever we need. So that's the sum, k equals 0 to infinity of negative 1 to the k, 2x to the 2k plus 1 over 2k plus 1 factorial. And if we wanted to, we could even multiply the x to the 7th in. So sum k equals 0 to infinity. We have negative 1 to the k. Then we have 2 to the 2k plus 1. I'll go ahead and write that as 2 to the 2k plus 1. Then we have x to the power 2k plus 1 and x to the 7th, which makes x to the power 2k plus 8. All over 2k plus 1 factorial. All right, that's the first term. No surprises, we're going to do something very similar for the second term. The only difference is instead of the sine, now we're going to work on the cosine. So, I know how cosine x works, so everywhere I see an x, now I'm going to put in 3x, because I want cosine 3x. So this is x to the 6, summation, k equals 0 to infinity, negative 1 to the k, 3x to the power k, divided by, power 2k, divided by 2k factorial. So this becomes, multiplying the x to the 6 inside, negative 1 to the k, 3 to the 2k, then x to the power 2k plus 6, divided by 2k factorial. All right, where are we at? Well, we now have the following. The basic fact about Taylor series tells us that the sum from k equals 0 to infinity of the kth derivative evaluated at 0 over k factorial x to the k, that's going to be equal to our function f of x. But it's also equal to the following pair of sums. Sum 0 to infinity of negative 1 to the k, 2 to the 2k plus 1, x to the 2k plus 8, over 2k plus 1 factorial plus the sum k equals 0 to infinity of negative 1 to the k, 3 to the 2k, x to the 2k plus 6 over 2k factorial. Now at this point you're probably thinking, maybe I should have just started taking derivatives. I only have to take 20. This is taking a long time. And it's not even clear that we're close. But we're almost ready to read off our answer. We've done all the hard work. So, how do we finish off? What's left for us to recognize? Here's the key observation. We're after the 20th derivative at 0. Where does that show up in this equation? Well, the only place where it has derivatives evaluated at 0 is over here, and saying that's the basic thing that Taylor series comes from. And so what we see is that if I want to have the 20th derivative evaluated at 0, well, that's from k equals 20 on this sum on the left-hand side. Now, if k equals 20, what do I see? Well, I see the 20th derivative evaluated at 0 divided by 20 factorial x to the 20. Okay, so here's the cool thing. Think of these two sides as just really big polynomials. Because in essence, that's what you're doing when you're thinking of series. How do you know if two polynomials are the same? Well, the answer is, look at their coefficients. If the coefficients match, they're the same polynomial. And so, we're going to look over here. What's the coefficient of the x to the 20? And the answer is, you plug in k equals 20. It's the 20th derivative at 0 divided by 20 factorial. That has to be equal to the coefficient of x to the 20 from this part plus the coefficient from x to 20 of that part. So I just need to find these coefficients, and then those have to match. So let's think about it. I want x to the 20. I have, for the x, it's to the power 2k plus 8. When does 2k plus 8 equal 20? At k equals 6. So here, we're going to be choosing k equals 6. So if we plug in k equals 6, we're going to get minus 1 to the 6, which is 1. Then we're going to have it 2 to the 2 times 6 plus 1, which is 13. And then here, x to the 20, but I'm just grabbing the coefficient. Divide that by 2 times 6 plus 1, which is 13 factorial. Plus. All right, what happens here? Well, here I have this to the power 2k plus 6. Well, when does 2k plus 6 equal 20? So what? 7. 2 times 7 plus 6 gives us 20. So if I want to get the coefficient of x to 20, I'm going to say what happens when k equals 7? So I'll have minus 1 to the 7. So that's a minus 1. 3 to the 14. And then I'll have x to the 20, but I'm just grabbing the coefficient right now, divided by 14 factorial. What's left to do? Well, we just want the 20th derivative evaluated at 0. What we've just discovered by comparing the coefficients is we found the 20th derivative at 0 divided by 20 factorial. What can we do to get rid of the 20 factorial? Well, multiply by 20 factorial. And if you do that, the 20 factorials cancel. This is what we want, which means that's our answer. 2 to the 13th over 13 factorial minus 3 to the 14th over 14 factorial, all that times 20 factorial. That's it. That's the answer. Now, it took us some time, but the idea is not so bad, because we did it for the 20th derivative. We could have done it for the 100th derivative or the 1000th derivative. The ideas are still the same. So look for the pattern. Grab the coefficients. And that's what we can do. So if you see any question that asks, find some derivative, what you're really going to do is find the power series for your function and learn to grab the right coefficient. Grab the right coefficient and you'll get your answer. All right. Find the interval of convergence for the power series, summation 7 to infinity of negative 1 to the n, x plus 5 to the n log n quantity squared. All right. Well, back to a good interval of convergence problem. What technique do you want to use? Root test or ratio test? Root test. I could have predicted that because people love the root test. Okay. So we're going to take a limit as n goes to infinity of absolute value a sub n to the 1 over n, which is the limit as n goes to infinity. Well, the negative 1 to the n, that's really gone. Absolute value of x plus 5 to the n to the 1 over n becomes absolute value of x plus 5. Downstairs you get n to the 1 over n, and you end up with log of n to the 1 over n squared. Well, absolute value of x plus 5 is absolute value of x plus 5. What happens to your denominator? If it helps, the first part you should know. N to the 1 over n? Yeah, it goes to 1. Now log of n to the 1 over n, well, this is certainly bigger than 1 to the 1 over n because log of n is going to get big. And it's also going to be certainly less than or equal to n to the 1 over n because log of n does not get very big very fast. That's 1. That's going to 1. Whoops, that's a 1 over n. Which means that this also goes to 1. All right. Well, that says our limit is absolute value of x plus 5. So, what do we know? Well, we have that the limit of a sub n to the 1 over n is absolute value of x plus 5, so this will converge when absolute value of x plus 5 is less than 1. Or another way to say this, when x plus 5 is between 1 and negative 1, and then if we subtract 5, so negative 6 less than x plus 5 less than negative 4. We're not done yet because we're asked for an interval. Now this is an interval, but what haven't we checked? We haven't checked the ends. The endpoints. Well, let's check the endpoints. We'll start with negative 6. So we plug in x equals negative 6. Now, one thing that you should know for sure is before you start, it better not be a root test or a ratio test. Because if you can apply a root test or a ratio test and get an answer, you've done something terribly wrong. Negative 6 plus 5 is negative 1. So negative 1 to the n times negative 1 to the n over n log n squared. So this is the summation 7 to infinity of 1 over n times log of n squared. Does this converge? Does this diverge? Or how can we help figure out the answer? One over n diverges, but this is not 1 over n. It grows just a little bit faster. Log n doesn't grow fast, but it does grow faster than nothing. The question is, does that log n squared there, is it enough of a boost? Does it just sort of put us just past the edge? That's a good question. That's why we ask these questions. How can we figure it out? What test can we use? Comparison is probably a natural test to think of, but comparison with what? You can certainly say this is smaller than 1 over n, but unfortunately that doesn't help because 1 over n diverges. Being below something that diverges is not quite enough. So this is that rare time when we pull out a particular test. Any other guesses? Not comparison. I'll tell you what else it's not. It's not limit comparison, or your nth term test, or root test, or ratio test, or alternating series test. What? Oh, the integral test. That's a nice idea. We should try that one. Okay. So why integral test? Well, one of the things is, if you want to know whether or not to use integral tests, ask yourself the question, would I want to integrate this? So you're getting to the point where you've done a lot of integrals. So you can almost get to the point where you can start to answer questions like, would I integrate this if I wanted to, or if I had to? And the answer, hopefully, is, I might. Okay, so could we integrate 1 over x log x squared? And the answer is, yes, we can. Because 1 over x is the derivative of log x. So this is good for a u substitution. U equals log x, then du is 1 over x dx. So this becomes the integral of 1 over u squared du. Update the bounds, log of 7 to infinity. Do we know the integral of 1 over u squared? Yeah, it's minus 1 over u. And we're going to evaluate log of 7 to infinity. Well, minus 1 over infinity, which of course means what happens to 1 over u as u goes to infinity? It goes to 0. That's useful. Everything else is just sort of, whatever. Minus 1 over log 7. Because I really don't care what happens at the other end. I just care about what happens as I head to infinity. Do I get something finite or not? In this case, I do. So the integral is finite. What does that say about the sum? Yeah, the sum is finite. So this converges by the integral test. So that tells us that we're going to include -6 in our interval. Now, we're not done. We have to plug in -4. But if you plug in -4, what you'll end up with is you'll get -4 plus 5 is 1. So you'll end up with -1 to the n over n log n squared. Now, in this case, we don't need to do anything because we know this is absolutely convergent because we did the sum without the negatives. So if you can do the sum without the negatives and it converges, then you know that this sum also converges. So absolutely convergent, which means we also include the other endpoint. So our final answer, -6, less than or equal to x. Oops. Why did I put plus 5 there? That should be there, gone. -6, less than or equal to x, less than or equal to -4. There we go. All right. Good. Using the ratio test and then checking endpoints, we find that the following series, the sum k equals 0 to infinity of ak x plus 4 to the k, has interval of convergence -9 less than or equal to x less than or equal to 1. So there's two parts. What's the value of the limit as k goes to infinity of ak plus 1 over ak? So, well, let's think about what this finds. So generally speaking, what this finds is we end up with something. It's going to be, okay. We have to think a little bit. This is a sort of a thinking question. And this did come from a real test. This was from a final exam from a few years ago. So they like to throw these on. So we should think about what's going on here. Well, before we get too excited, let's sort of go backwards. So -9 less than or equal to x less than 1. That tells the following. It says, okay, our interval of convergence, -9 up to 1. Now, the terminology for our intervals of convergence, they kind of sound like circles, because we say about things like the center and the radius, because they are circles. They're one-dimensional circles. So let's think about some things that we can say. Where's the center at? Yeah, it's at -4. Now, that should not be too surprising, because that x plus 4. So x minus -4. So our center is at -4. Now that you see the center, what's the radius? Yeah, it's 5. You go out 5 in both directions. So, now we come to this question, well, what is the value of this expression? Well, if we think about what we want here, this limit, whatever it is, it's going to be absolute value of x plus 4 over something. Oh, sorry. Let's be careful here. So if I were finding the radius of convergence here, what would I do? I would take a look at the limit as k goes to infinity. I would look at ak plus 1, x plus 4 to the k, divided by ak, k plus 1, sorry, x plus 4 to the k, absolute value, that's the ratio test. So this would be the limit as k goes to infinity of the absolute value of ak plus 1 over ak times the absolute value of x plus 4. So we have this limit times this absolute value of x plus 4, and that will be converging, or it converges, whenever this is less than 1. So the limit as k goes to infinity of absolute value of ak plus 1 over ak times absolute value of x plus 4 less than 1. This gives us information about this expression here. Now, let's sort of say what's true. We know that this will converge when absolute value of x plus 4 is less than 5. This 5 is our radius of convergence. These two statements have to be compatible. Well, what does that say about our limit? Well, another way to say this is 1/5 absolute value of x plus 4 less than 1. That's when we know it will converge. So now we just play our matching game. This limit has to be 1/5. In general, what's true is that when we take this limit here, in general, this will be 1 over our radius of convergence. So the answer for part A is 1/5. All right. Now we get to part B. What is the interval of convergence of the power series, the summation k equals 0 to infinity, 2 to the k, a to the k times x minus 3 to the k? Okay, now this one is going to be interesting. Let's think about what we actually know. If you go and just think about the interval of convergence, what does this say? It says that the summation k equals 0 to infinity of a to the k, z to the k, and I'm just right now, z is just any generic thing. When will this converge? Well, according to this, I look and say, what happens to x plus 4 between -9 and 1? What's the smallest that x plus 4 can be? Well, the smallest would be at -9. So this will converge as long as I have -5 is less than or equal to z. And the largest it could be was at 1, which is 5. So if I was just looking at ak times something to a power k, that will converge whenever that z thing is between -5 and 5. And -5 is okay. -5 is okay. Essentially what I'm doing is I'm just doing a shift here at my center. If we look at part B, what do we say? Well, for part B we have the sum, k equals 0 to infinity, and I can rewrite this as ak times 2x minus 3 to the k. So this will converge when what's true? Well, when -5 is less than or equal to 2 times x minus 3, and that's less than +5. At this point, we can now do some simple things. We can divide everything by 2. -5 halves less than or equal to x minus 3 less than +5 halves. And now add 3 to everything. -5 halves add 3 would be 1/2 less than or equal to x less than 5 halves add 3. That'll become 11 halves. So the answer to part B is 1/2 less than or equal to x. Sorry, that's off the bottom there. 1/2 less than or equal to x less than 11/2. Okay, this is not the same flavor of problem. It's a different type of problem. But you should prepare for these types of problems. What's being tested here? What's being tested here is, do you understand how interval of convergence works? So let's think for just a moment. Let's do like a 2-3 minute talk about interval of convergence ideas. I think this is useful to understand. Okay, so a quick 2 or 3 minute talk about interval of convergence. So generally speaking, what's true is if I have a sum k equals 0 to infinity of ak something to the k power, well, what's going to be true is I'm going to have my center in this format will be just at 0. And now, when you look at it and you say, suppose I know it converges. So suppose it converges at some point. So there's some number here, I don't know, let's call it t. So I know that when I plug t in, the sum k equals 0 to infinity of ak t to the k, that is a convergent sum. See, that gives us information. What information does it tell us? Well, if I know something converges, then I know that it's growing small enough that it's going to go to 0 to allow me to converge. So one of the things it tells me is it says anything that's getting smaller even faster will also converge. So if I have one place where it converges, then I automatically know that anything smaller than it converges. So that tells me as a free bonus, all the way down to 0, I must converge. Because if I look at what's happening, I'm going to get a smaller term here. That whatever point I pick grows at a smaller rate. Now you might say, do I get anything more? And the answer is I do get more. What else do I know? Well, the answer is anything on the other side also will converge up to negative t. Now I don't know what happens at negative t. It's not quite enough. All I can say is anything smaller than it will also converge. And that's just looking at a root test or a ratio test. It also has to converge. What if I know, so we don't know about that point. What if I know that something must diverge? So over here, let's say this is our point S. The summation k equals 0 to infinity ak s to the k. Suppose we know that this diverges. What does that say? Well, it says that it doesn't go to 0 fast enough. So if I don't go to 0 fast enough, then I have a problem. Well, what happens to the stuff over here? What's true? It must also not go to 0 fast enough, because it's worse, because this is larger in size. So anything larger in size must diverge. So if you know one point diverges, anything larger than that size must diverge. But of course, the symmetry also says the same thing, anything over here. There's a chance you don't know. So you should understand how things work for interval of convergence. It's always the convergence comes down to a question of size. Are you growing to 0 fast enough, or are you not? All right, so be prepared to answer some type of question. Who knows? Who knows what's happening? All right, determine if the sum n equals 1 to infinity cosine pi n log of n plus 1 minus log n diverges, conditionally converges, or absolutely converges. Well, what do we do? Now, here, we're trying to obfuscate some things. When I say obfuscate, cosine pi n, what's another way to say of cosine pi n? Well, normally cosine is an oscillating function. But when we're doing sums, we don't look at every value. We look at particular values. So it's like cosine pi, cosine 2 pi, cosine 3 pi, cosine 4 pi. So cosine pi n is secret code for negative 1 to the n. So what we have here is there's an alternating sign coming into play. Now, what about log of n plus 1 minus log n? Well, it can be written as log of n plus 1 over n. Now, it's not clear that that's helpful, but if we think about this in terms of an alternating series, the question becomes, what happens to this? Now, in subtraction, it's not so clear, but when you write it as log of n plus 1 divided by n, what does happen to log of n plus 1 over n as n goes to infinity? The inside goes to 1, and log of 1 is 0. So it alternates, and it goes to 0. So what can we conclude? Well, we can conclude that it converges. By what test? Alternating series test. So we are now in the place that we can say with great confidence, it's not diverging. We've knocked one choice out. We still have choices left. So we have to think about, okay, is this conditional convergence or absolutely convergent? Okay, well, to figure that out, drop the alternating sign. So look at the sum, n equals 1 to infinity, of log n plus 1 minus log n. Okay, this looks like something that should telescope, because it's something that should telescope. So that's a good reason to look like that. Now, unfortunately, if we look at our pieces, this is not going to 0. So that's bad news. In fact, it's really bad news. Not only does it not go to 0, it doesn't go to a number. Where does it go to? It actually gets bigger and bigger. That's very sad. We know what's happening. We can already predict the future. But let's go ahead and write down the first few terms. So when our terms don't go to 0, if you look at the partial sums, so you get log, I'll start with 2, log 2 minus log 1. Then you're going to, next case, it'll be log 3 minus log 2, and log 4 minus log 3. And you're going to go for a while, and we'll stop somewhere just to sort of catch our breath and see what's happened. And if you start looking at the terms, you'll see that, well, the log 2's cancel. And you should expect cancellation off by 1. The log 3's cancel. Log 4 will cancel with the next one. And then here, this log n will cancel with the one that came before. And log of 1 is also known as 0. So the partial sum is log of capital N plus 1. And what happens to log of capital N plus 1 as capital N drifts off to infinity? It's infinity. This diverges. Okay, so sum diverges. In general, if you do have something that looks telescoping, where the part that telescopes, if it goes to 0, you don't just have to look at the first few terms to see what cancels. If it doesn't go to 0, look at the first few terms, then look at what's happening to the terms at the end in a partial sum. And then you'll figure out, okay, what happens. And then if the terms go to infinity, okay, you're out of luck. It's going to diverge. It's going to diverge. So when we drop the alternating sign, the sum diverges. So what can we eliminate? Yeah, absolute. And we don't even have to say eliminate. Now we know the answer. So this is conditional. Conditionally converges. All right. Good. Well, for each of the following infinite series, determine whether the series converges or diverges, and justify your answer. Okay, so here, let's start with this first one. The first one looks terrible. The sum j equals 10 to infinity, 3j minus 2 over the square root of j to the 5th plus 2j plus 4. And you're just like, how are we going to find it? Well, this has a lot of noise. Get rid of the noise. So, how do you get rid of the noise? Do a limit comparison. If you do limit comparison, all you need is the fastest growing terms. And so in our case, what are we going to compare it to? Well, the top, the fastest growing term, is 3j. In the bottom, it's the square root of j to the 5th. So this becomes the sum, j equals 10 to infinity. I can pull the 3 out, and j over j to the 5th is 1 over j to the 3/2 power. Now, is this sum converging or diverging? Converging. Why? Yeah, converges, because this is a p-series. It's a p-series where p happens to be equal to 3/2. So, the sum converges. By limit comparison, they're tied together, and so the answer is this converges. All right. Now, could you have done other tests? Yeah, you probably could have done a straightforward comparison test. But I like limit comparison. Limit comparison says just get rid of the noise. All right, B. 5 over 3 minus sine of r to the power r. Well, that's really different. Now, the problem is, sine of r, this is hard to predict because it'll move around. Sometimes it'll be very small. Well, very small, mean what? -1, right? It'll go somewhere between -1 and 1, but it's hard to predict where it will be. So it's not so clear. However, what we can say is, well, let's think about it. It almost looks like geometric, except the thing is that it's something over to a power r. The 5 upstairs won't have any influence. It's just a constant. So what do we say? Well, 3 minus sine r, it's not arbitrary. It can't be huge. The most it can be is 4. And the least it can be is 2. So it's somewhere between 2 and 4. So in worst case scenario, the largest that this part could ever be is something over 2 to the r. Now when I say largest, if I want the downstairs to be, if I want the whole thing to be large, I want the downstairs to be small. So that's why I'm pointing to the 2. So 5 over 3 minus sine of r to the r power is below 5 over 2 to the r. And it's certainly above 0. What do we know about the summation of 5 over 2 to the r? Does this converge or diverge? And how do we know? This sum converges. But how do we know it converges? What are we doing? It's what? Geometric. It's geometric. This is a geometric sum. And in our case, it's a geometric sum where it's a 1/2. So it's really like 5 times 1/2 to the power r. So I can bound this below something which converges. So by comparison test, this also converges. Now you might say, wait a second, I thought, shouldn't we have at least one of them diverge? Whoops. Shouldn't we have at least one of them diverge? See, I was preparing to do my statement here. Look, it's possible that all your sums might converge, or they may all diverge. Don't try to be like, ha. Well, this one converged, so the other one better diverge. No. Don't think that way. That's a dangerous way to think. And do you know how I know that? Because we know you think that way. So we know how to play. And we're really good at playing fun mind games. All right, rounding the corner, we're almost there. Find the interval of convergence for f of x is 27 times 2 minus x to the power 3n over 8n times square root of n. Okay, so what do we do? Well, we'll think of this as our a sub n. So we're going to do our root test, limit n goes to infinity of absolute value of an to the 1 over n, which is the limit as n goes to infinity of 27 to the 1 over n. Then I'm going to have absolute value of 2 minus x cubed, because I have to the power of 3n to the 1 over n becomes just to the power of 3. Downstairs, 8n to the 1 over n becomes 8. And then square root of n is the same as n to the 1 over n to the 1/2. So I'm taking the nth root of the square root. And in here, we can see a couple of things. N to the 1 over n goes to 1. 27 to the 1 over n, well, that also goes to 1. So 27 was sort of thrown in there as a little bit of a red herring. And, well, some people weren't paying attention. 27 doesn't have any influence at all on this problem. So limit as n goes to infinity. There's no more limit. We already did the limit. So we end up with 2 minus x cubed over 8. So this will converge when this is less than 1. So we get that 2 minus x, absolute value cubed, is less than 8. That's the answer for when it converges. Now, I'm taking absolute value, so instead of saying absolute value 2 minus x, I can just say absolute value of x minus 2. That's the same thing. And I just like to do that because I'm used to that mindset. You know, absolute value of x minus a. How do I get rid of the cubed? Cubed root. So absolute value of x minus 2 needs to be less than 2. Or x minus 2 is between 2 and negative 2. And now if we add 2, we're going to end up saying that 0 is less than x is less than 4. So we know for sure it converges between 0 and 4. Now what we don't know is what happens at 0 and what happens at 4. That's the only two mysteries left. So let's go ahead and solve our mysteries. So at x equals 0, we're going to get the summation 1 to infinity of 27 times 2 to the 3n divided by 8n times square root of n. Well, 2 to the 3n, what's another way to think of that one? It's like 2 cubed to the n, or 8 to the n. So these are actually set up to cancel. So we end up with a summation, n equals 1 to infinity, of 27 over square root of n. Does this converge or diverge? Diverges because it's a p-series. And it's a p-series where p equals 1/2. Now, what does that tell us? That says 0 is not going to be in our interval of convergence. Okay, so that means we just have one more point to go. At x equals 4. So we plug that in. Summation n equals 1 to infinity. 27. Then we get 2 minus 4 is negative 2 to the power of 3n over 8n square root n. So this becomes summation. The only thing that changes is that negative. So we have to think about this for a minute. Well, the 2 to the 3n and the 8 to the n still cancel. The 27 is still 27. The square root of n is still square root of n. But now we have to think of this minus. So let's just do some sort of work on the side here. Negative 2 to the 3n. It's like negative 1 to the 3n times 2 to the 3n. And the 2 to the 3n will become 8 to the n. Now, negative 1 to the 3n, we can think of this as negative 1 cubed to the n. Because I really like to think of things to the n power. And negative 1 cubed is negative 1. So this becomes negative 1 to the n. Which means it's a little different. We have this plus minus thing going on. So we have a plus minus. So it's alternating. Do our terms go to 0? In other words, does 27 divided by square root of n, does that go to 0? I know, we're almost there. Come on, just one more problem after this one. 27 divided by square root of n goes to 0, yes or no? Yes! Okay, good. Okay. So, this alternates, and terms go to 0. And so what's our conclusion? So it converges. Converges by alternating series test. So you should be ready to give names. So if anything says justify, be ready to write down what test you're using. Is it the alternating series test? Is it the integral test? Is it comparison? If it says don't justify it. All right, which means we do include the endpoint of 4 because it converges at 4. So our final answer is it converges 0 less than x less than or equal to 4. All right, our last problem, I think. Find the exact value. Well, we started with a couple of find the exact values, so it's good to end with a find the exact value. So find the exact value of n factorial plus e to the n over n factorial times e to the n. Well, that's interesting. Well, what can we do? We can split them, yeah, because you see there's a plus here, so the natural thing is to break this into two sums. So we're going to have n factorial over n factorial times e to the n, then plus a summation n equals 0 to infinity of e to the n over n factorial e to the n. Now in the first sum, the n factorials cancel. So this is the summation n equals 0 to infinity of 1 over e to the n. Now that's good. That's geometric. We can handle that. The second sum, n equals 0 to infinity, the e to the n's cancel. So it's 1 over n factorial. Now that's a little different because that's not geometric. Now comes the time when you're like, well, wait a second. 1 over n factorial. That reminds us of things. And the e is another hint. The e to the x is the summation k equals 0 to infinity of x to the k over k factorial. Now I chose k, I could have chosen n. So, well, let's say I did choose n. Sum n equals 0 to infinity, x to the n over n factorial. The symbol we used for our index doesn't matter. These look almost the same. And they are the same if we do what? Well, choose x as 1. Because if we choose x as 1, 1 to the n is 1. So, if we choose x equals 1, we get that e to the 1, which is e, is the summation n equals 0 to infinity of 1 over n factorial. So this second sum is e, and it comes from recognizing it as a Taylor series evaluated at a point. That's why you want to be familiar with Taylor series. This first sum, well, that's 1 over 1 minus 1 over e, because that's our rule for geometric sums. It's 1 over 1 minus what you multiplied by. And the reason it's 1 is we start at 0, which is our first term. Now we can simplify this. Here, if you multiply top and bottom by e, you'll get e over e minus 1 plus e. And you could even, if you wanted to, if you multiply this by e minus 1 over e minus 1, so you get a common denominator, you'll get e plus e squared minus e all over e minus 1, giving us our final answer for the day, e squared over e minus 1. And that's our last one. Whew. Good luck on the exam, and see you later.